Alright, now I want to go over 11.7, which is exponential and log equations. There's a lot of steps, so we're going to first talk about the handout that it's posted on D2L. So we're going to talk about solving exponential equations where the bases can be made equal. You write the equation as b to the m equals b to the n, meaning you make the bases equal. You drop the bases, so you get m equals 1. We can do that because exponential functions are 1 to 1, and then solve for the unknown. So for example, on this case, say we have to solve 3 to the x minus 2 equals square root of 3. You can see the base on the left side is 3. We can write the right side as 3 to the 1/2. And now, because exponential functions are 1 to 1, we can drop the bases. So x minus 2 equals 1/2. X is 2.5. Okay, another example. 2 to the x squared minus 7 equals 2 to the 6x. You can see the bases are already the same, so we can drop them. This time we get a quadratic equation. We set it equals 0 and put it in order and factor it. Luckily it factors. X minus 7, x plus 1 equals 0, so we get two solutions, 7 and -1. Now sometimes it's a little bit tricky, like if you have 8 to the 4 minus 2x equals 4 to the x plus 2. The base on the left is 8, the base on the 4 is 8. We cannot make 8 as a 4 to a power, but what we can do is we can make of them, the root base is 2, so we can make this 2 cubed, 4 minus 2x, and we can make this 2 square, x plus 2. Now the power to power rule allows me to distribute the 3 into 4 minus 2x, so I get 12 minus 4x, and distribute the 2 into x plus 2, so I get 2x plus 4. Now we have the same base, so we drop the base. We get 12 minus 4x equals 2x plus 4. Subtract the 2x. 12 minus 6x equals 4. Move the 12 over. Negative 6x equals it's 12 minus 6x, sorry. That's negative 8x equals 8. Negative 8, so x is 1. So please fix that, okay? Alright, so that's if the bases can be made the same. What if the bases cannot be made the same? Exponential equations, again, this is the handout that's posted in D2L. Exponential equations, and it's also in the notes that I post on D2L. If one base is 10, then take log of both sides of the equation. For example, if you have to solve 10 to the 3x equals 2.1. This is a base 10. To get rid of base 10, we do log base 10 of the left side equals log base 10 of the right side. Again, the reason we can do this because log functions are 1 to 1. If x1 equals x2, then log of x1 equals log of x2. That cancels out, and now the exact answer would be log 2.1 over 3. If they want the exact answer, you stop there. If they want you to round off your answer, then you put it in your calculator. So we do log of 2.1 divided by 3, and it's roughly 0.1074 if they're asking for 4 decimal places. 1074. If one base is 10, you use log. If one base is e, you use ln because you want to get rid of e, so you use ln. So here's an example about base e. e to the 2x minus 2 equals 50. So we want to isolate e to the 2x first. By adding the 2 to 50, we get 52. Since the base is e, we ln both sides, so we get 2x is ln of 52. Exact answer is ln of 52 over 2. Or if they want decimal answer, we put it in our calculators. And 4 decimal places, 1.9756. Now, what if the base is neither 10 nor e? Then it's your call. You can take ln or log base 10 of both sides and then solve. So for example, this is going to be a little bit more work if the base is neither 10 or e. 6 to the x minus 1 equals 2. So first we want to isolate 6 to the x minus 1 by adding the 1. We get 2 plus 1 is 3. Since I prefer to use, it doesn't matter, log or ln. That's not going to cancel out because the bases are the same, but we can take this and times it by the log using the power rule for log. And then divide log 6. You want to isolate x. So you divide log 6. You get x minus 1 is log 3 over log 6. And then you add 1 to get your final answer. Again, this would be the exact answer. If they're asking for estimate, then you put it in your calculator. Log of 3 divided by log of 6 and then plus 1. And you can see it's 1.6131. So x is roughly 1.6131. Okay. Another example. 3 to the x plus 2 equals 7. So we move the 2 over. 7 minus 2 is 5. Since the base is neither 10 nor e, we do log or ln. I prefer to do log, but you can do ln. It doesn't matter. So x equals log of 5 over log of 3. Exact answer or estimate. 1.4650. Okay. Now if we do something like this, this is one of the tough ones. Solve for x. 3 to the x equals 2 to the x plus 1. Well, the base is neither 10 nor e, so we're going to do log of both sides. The power rule tells us to take this and times it by the log. X times log of 3 equals x plus 1 times log of 2. So now we cannot divide by log 3 because we have x on both sides of the equation. So we're going to distribute, just like having a 2, we distribute it. So having log 2, we distribute it. X log 2 plus 1 log 2 equals x log 3. So we want the x terms to be on one side, so we move this over here. So subtract it. X log 3 minus x log 2 equals log of 2. So I subtracted x log 2 basically. Okay, and I can pull out the x to get log 3 minus log 2 times x equals log 2. And now I can divide by log 3 minus log 2. And that would give me x isolated. And now I can put it in my calculator to get the exact answer. Log of 2 divided by log of 3 minus log of 2. And it's roughly 1.7095. Okay, so now to log equations. There are, again, just like exponential, there are two types of log equations. The first type, again, the same handout. If you flip the page, solving log equations that have a non-zero constant. So you have a constant that doesn't have a log in front of it. You separate the logs from the constant. So here, for example, if I say solve and check, in this case you must check your answer when you do log, because log of negative or log of 0 is undefined. So you must check. Okay, so if you look at log of x minus 1 plus log of x minus 4 equals 1. This is the case that I'm talking about, solving log equations that have a non-zero constant. 1 is a non-zero constant. It doesn't have a log in front of it. This has a log, this has a log. So the first thing, you separate the logs from the constant. They're already separated. And then use the properties of logs to combine multiple logs into a single log. If it's a plus, changes into times. If it's a minus quotient, if you have a number in front of it, you put it as a power. So this is a plus, it changes into times. So we're using the first rule, x minus 1, x minus 4 equals 1. The next step, change the log form into exponential form. We look at the base, remember how we did that? We go across 10 to the 1 equals x minus 1, x minus 4, and we drop the log because now we're in exponential mode. And then solve, and you must check your answer. So FOIL it, x squared minus 4x minus x plus 4 equals 10. X squared, add like terms, minus 5x, 4 minus 10 is negative 6. Factor it, a product of negative 6, a sum of negative 5. So negative 6 and 1. You check your answer, you only check it back into the original equation. As long as you do log of positive, you're okay. So if you put a 6 here, 6 minus 1 is 5. We can do log of 5 and get an answer. 6 minus 4 is 2. We can do log of 2 and get an answer. If you do negative 1, that's a problem because negative 1 minus 1 is negative 2. If you try to check it and do log of negative 2 on your calculator, it's going to tell you it's an error, non-real. So that's why it doesn't check. So this doesn't check, and this checks. Let's try another one of those where there's a constant without a log, ln of x squared minus x minus 6 minus ln of x plus 2. Again, the logs are separated from the constant. We have a minus, and that means we're using the second rule, which is the quotient rule. So you're going to do log of the top over bottom, log of the top, the plus over the minus. Now we can actually factor that, and luckily when we factor it, we can cross out x plus 2. So it's a lot easier. So ln, remember ln is log base e. Why do I write it like this? Because now I want to do exponential. E2 equals x minus 3. Add the 3. E2 plus 3 equals x. This is exact answer. E squared plus 3. So it's roughly 10.3891. Here's another one. Again, solve and check. 2 log base 3 of x minus log base 3 of x minus 4 minus log base 3 of 2 equals 2. We have multiple logs, no log on this side. They're separated. The first thing we do is put that as a power. So we get x squared minus log base 3 x minus 4 minus log base 3 of 2. Now since we have minus minus, to put it as a single log, x squared has a plus, we put it on top. This has a minus on the bottom. The 2 has a minus on the bottom. Okay, and then we change it into exponential. 3 squared is 9 equals x squared over 2x minus 8. And then drop the log because now we have exponential mode. And then we can multiply by 2x minus 8 to get rid of the fraction. So we get x squared equals 18x. 9 times negative 8 is minus 72. We want to move everything over to get a quadratic equation in general form. x squared minus 18x plus 72 equals 0. Now factor it. So it factors into x minus 12, x minus 6 equals 0, x equals 12, x equals 6. We're gonna check again, make sure we don't have log of 0 or log of negative. If you put a 12, that's log of 12. 12 minus 4, that's log of 8. No variable there, so that works. 6 is good. 6 minus 4 is 2 is good, so we're good. So both of them check. What if the log equation does not have a constant, if it's all logs? Solving log equations that don't contain a non-zero constant, use the properties of logs to write the equation with a single log on either side of the equation. So you're going to have log of something equals one log of something else. Again, one log on this side, one log on that side, for example, before we go to the next step. So if I have log of x minus log of x minus 1 equals log of 3. So you can see every one of them has a log in front of it. To make this a single log, we use the quotient rule. So we write log x over x minus 1 equals log of 3, and we have log on either side. Drop the logs because logs are one-to-one functions. If log of a equals log of b, then a equals b, so x over x minus 1 equals 3. Solve, and you must check your answer again. So to solve, you're going to times by x minus 1 to get rid of the fraction. So you get x equals 3x minus 3 minus 3x. Negative 2x equals negative 3. Divide by negative 2. The negatives cancel out. If you put log of 3 over 2, it's good. 3 over 2 minus 1 is 1/2. It's good. So we got a solution. Okay. Another example, log of x plus 4 plus log of x minus 4 equals log of 9. There's two logs here with a plus, so that changes into times. Log of x plus 4, log of x minus 4 equals log of 9. We can drop the logs and FOIL this. X squared minus 16 equals 9. We can use the square root method by adding the 16. So x equals 5 or negative 5. If you check the 5, 5 plus 4 is 9, 5 minus 4 is 1, so it's all good. If you check the negative 5, negative 5 plus 4 is negative 1. If you do log of negative 1, it doesn't work. So we got one solution. Okay, now for applications, again, we're still in 11.7. It's a long section. So I'm going to do applications, but I want to review for exponentials and then do logs. So we did in exponentials, we did continuous compounding formula, which is paired. A equals paired. That's an example of exponential growth. Where P is the principal, it's the amount you invest or borrow. A is the balance, that's what you end up paying or keeping. R is the rate of growth in this case, or decay. And T is the time. And we also talked about time to double your money. T equals ln of 2 over r. Okay. Now for exponential decay, instead of growth, it's exponential decay, like radioactive substances. They decay exponentially. So we use similar formula to paired but different notation. A sub 0 e to the kt. K instead of R, A0 instead of V. Since we're talking about radioactive substances, A0 is the amount of radioactive substance uh, it's it's the initial amount, which is at time t equals 0. Once you start the experiment, how many grams of uranium did you have? 20 grams, 5 grams? That's your A sub 0. K is the rate of decay. And K is negative because, decay means negative, okay? Negative rate. T is the time, and A is the amount remaining. In the case of money, you have growth, so you get balance. In the case of decay, you have amount remaining. You start with 20 grams, you end up with much less grams, 15 grams, 10 grams, we don't know. Now, instead of time to double your money when you're growing, it's time to cut your substance in half, which is called half-life. It's the half-life of a radioactive substance. The half-life of a radioactive substance is the amount of time needed for initial amount A sub 0 to be cut in half. Cut in half. That means half will remain. Because half will decay, that means half will remain. So for instance, if you have 20 grams of uranium after a half-life, could be 10 years, 10 million years, we don't know, it's 10 grams. After another half-life, it's 5 grams, and so on. And the half-life formula T is, instead of ln of 2 for doubling the time, ln of 1/2 for cutting in half. Instead of R, we have K. That's how you figure out the half-life formula, to find the half-life. Alright, so if you look at some examples, 104, page 985. It says, in 2 years, 20% of radioactive element decays. 20% decays. Remember, we're only interested in what remains, so 80% remains. Okay? Find its half-life. That's what we need. So to find T, remember T is what? ln of 0.5 over K. We need K, the rate of decay. Okay, to find T, we need K. How do we find K? We go to the formula that I listed. E to the KT. So if 80% remains, the amount remaining is 80% of what? Of the initial amount. So if the initial amount is 100 grams, you can put any number. I'm making 100 to make it easy. So 80% of that is 80 grams. So if you do 100, that's 80 remaining. And if you divide, you're going to get 0.8. No matter what you do, which number you put here, if you do 80% and you divide it, you're always going to get 0.8. So if they tell you 80% remain, you're always going to have 0.8 here, okay? And then we have exponential equation. We can solve it. Since the base is E, we do ln of both sides. Remember, we spent time on this. KT equals ln of 0.8. T is ln of 0.8 over K. It's just like, see, when it's half remaining, ln of 0.5. When it's 80% remaining, which is 0.8, it's ln of 0.8. Same idea. So T, the half-life, is ln of 0.8. I mean, the time is ln of 0.8 over K. So to find K, okay, so now hold on. We need to find, so ln of 0.8 equals KT. We need to find we need to find K, but T is 2 because 80% remains in 2 years. That's what they're saying. Okay, so 2 years. So to ln of 0.8 equals 2K. So K is ln of 0.8 over 2. If you put it in your calculator, that's what you get. So now we put it in that formula to find the half-life. T equals ln of 0.5 over K. ln of 0.5 over 0.111572 with a negative, which is roughly 6.2 years. Okay. Let's look at 108. Another application, page 985. So it says C14 dating, only 10% of C14 in a small wooden ball remains. So scientists found a wooden ball and they measured the percentage of C14 in that ball and they found only 10% remains. They're not saying decay, so that's what remains. That's what we need. It's always what we need is what remains. How old is the ball? They want to figure out how many years has it been there. How old is the ball? So they need time. Okay, they need time. And we have the half-life that's given in the book for C14 is roughly 5,700 years. It takes a long time for C14 to be decaying in half. 5,700 years. Okay, to find how old is the ball if 10% remains, remember A equals A0 e to the kt. If 10% remains, so if you use 100 for initial grams, then 10% is going to be 10. Remember what I told you? You're going to have 0.10 here, no matter what, okay? And if you do ln of 0.10 equals kt, so we need k. You can't find the time, how old that ball is without k. In order to find k, we have the half-life. That's what we're going to use. Remember, the half-life is ln of 0.5 over k. Or k is ln of 0.5 over the half-life. So we can find k this way, since we have 5,700 years for k for the half-life. So ln of 0.5 divided by 5,700, and that's negative 1.216 times 10 to the negative 4, which is roughly negative 0.0001216. If you put that in there, t is ln of 0.10 over negative 0.0001216. So that ball is about 18,900 years old, which is pretty old. And that ends 11 altogether, 11.7. All right.